So today we're going to be looking at zeros and multiplicities. So again, the zero of a graph are the points at which the function intersects the x-axis, also known as the x-intercepts. Wait, that's just the note. Okay. A polynomial function of degree n can have at most n real zeros. So whatever your degree is the total amount of real zeros that are possible. An even degree polynomial has an even number of real zeros, or it could have no zeros as well. And an odd degree polynomial has an odd degree of real zeros, or number of zeros. So the first thing we want to do whenever we are working with these is we want to graph each equation. And so what we're going to do is plug in our calculator. So if you do not have a calculator yet, you should probably grab one. So we want to go to our y equals, and we want to plug in our equation.
Isn't it?
You owe me a quarter of my
So once we plug in our equation into y equals, or so we can graph it, what we want to do to make an accurate graph on our paper itself is, again, we want to look at our table. So second graph, that opens up our table. So if I'm looking at it, I can then take the y values and look at those. And so negative 12 is going to be too big, but I can grab from negative 2 all the way to 2, because those values on our y are not too big, and we can actually graph them on our graph. Just need to extend mine up to 8. So with these points, I can then put them on my graph. So I have negative 2, 0. So that's one of our x-intercepts. Negative 1, I'm at 2. 0, I'm at 0. 1, I'm at 0. And at 2, I'm at 8. So then we want to accurately draw our graph. And I can come up, down, and back. So the next thing it says is we want to graph it. We also want to identify its zeros. So there's kind of two different ways that we can identify our zeros. One, we can see where they cross the x-axis. Second way is we can look at our table, right? If our y value is equal to 0, we know we're on the x-axis, or we have an x-intercept or a 0. So we've got two different ways of looking. So my zeros for this one are at negative 2, 0, we're at 0, and at 1, we're also at 0. Now all of these have a multiplicity of 1. And we're going to find out why I know that here in a little bit. Let's look at our next equation. We've got negative x to the 4th plus 4x to the 3rd minus 2x squared minus 4x plus 3. So when we're looking at this equation, notice I kind of have an M shape on my graph. Again, we still want to start off with our XY table. We want to be able to grab points to then put onto our graph. So again, second table. This time it looks like I can go from -1 to 3 on my X values. And my Y values are 0, 3, 0, 3, 0. So when we plot those points, -1 I'm at 0, 0 I'm at 3, 1 I'm back at 0, 2 I'm at 3, and 3 I'm back at 0. So there is our graph. Again, we're just trying to identify the zeros here. So again, I can look at the table. I can also look at the graph, see where we touch the x-axis. So I have the zeros at -1, 1, and 3. Okay. So that's one way we can identify the zeros, right? We can look at the graph, we can look at the table. Another way that we can identify the zeros is by factoring. So we've been factoring before. So the linear factors of a polynomial reveal its zeros. Linear factors can be found by writing the polynomial in factored form. So if we want to look at number 3, we've got the problem x cubed minus 2x squared minus 15x. And so we want to factor that. How could we do our first step factoring? Divided by x, right? They all have an x in common. So greatest common factor is an x. When we take that out, we're left with x squared minus 2x minus 15. So then we can factor this new trinomial that we have. What would our signs be when we factor this one? Plus and minus. So we need two numbers that multiply to get 15, whose difference is 2. What two numbers? 5 and 3. And we need a -2. So that means we have to have a -5 plus 2. 3 gets us that -2. Now that we have it in factored form, the way we find our zeros from that is we set this equal to 0, and we take each of those factors, set them equal to 0. So x equals 0, that one's easy. X plus 3 equals 0, and x minus 5 equals 0. And we want to solve, so we subtract 3, and add 5 over. So we're going to get x equals a -3 and a +5. Now, there's an easy way to check. We just learned that we can also just look at the graph to find the zeros or those x-intercepts. So we can also check our work very easily by just plugging in our function into our y equals and graphing it. So if I do that, I can see on my graph that I do cross at -3, cross at 0, and I cross at +5, which are the zeros. Okay. Any questions on that? So then let's talk about the next thing, which is multiplicities. So the multiplicity of a 0 is equal to the number of times its corresponding linear factor occurs. So let's look at number 4. Number 4, we've got x cubed minus 6x squared plus 9x. How could we factor this one? what would be the first step? Take out an x, right? They all have an x in common. I'm going to take that out. What would be the next step? Again, we have a trinomial. So we want to split it up. X times x. What are our signs going to be for this one? Both negative, right? We have that positive c value, so we look at our b. Use the same sign as our b. It's negative. So we need two numbers that multiply to get 9 and add together to get 6. 3 and 3. So here we have a multiplicity, right? Our factor appears twice. So we really have x times x minus 3 squared. Our zeros, again, are, of course, we set each factor equal to 0. So we've got x equals 0. If I set x minus 3 equal to 0, what does my x equal? 3. Okay. Whenever we have a multiplicity, what we want to do is we don't want to just say 0 and 3, because that's leaving out information, right? We also want to say that 3 has a multiplicity, and we want to say how many times. So the way we list that is we're going to use MULT, so shorthand for multiplicity, and then how many times it occurs. So we can read it 3 multiplicity of 2, and we also have 0 as one of the x values. Now let's check. This is the way we can solve by factoring, but our calculator also tells us when we have multiplicities. So let's plug it in. We got x cubed minus 6x squared plus 9x. And so when we graph this, notice on our graph, we pass through at 0, but we said we have a multiplicity at 3, and notice it comes down and it bounces off. This means we have an even multiplicity. So on our previous problem, so number 2, we actually have a multiplicity here as well, and that's going to be 1. So 1 actually has a multiplicity of 2. And again, that makes sense. If we think about it, the amount of x-intercepts we have, possibly, is at most or equal to our number of our degree. Well, if we just have -1, 1, and 3, we're missing one of our x-intercepts. But if 1 has a multiplicity of 2, then we have all 4 of those, right? 1, 2, 3, and 4. Same thing over here. 1, 2, 3. We had a 3rd degree. We have 3 intercepts. Okay. So if it bounces, that means we have an even multiplicity. And if it's odd, then that multiplicity is going to pass through. So that's kind of our notes on that page. So if the multiplicity is odd, then the graph passes through. If the multiplicity is even, then the graph bounces at the 0. Okay? That makes sense? So let's look at a couple of these together. So number 6, they already have it factored for us. So what are our zeros on number 6? Again, if it's already factored, all we have to do is set those factors equal to 0. So we have x plus 7 squared to x plus 1 and x minus 4 cubed. We want to know the zeros, the multiplicity, and the effect at that 0. So first off, we already have it factored, so we can set each of these factors equal to 0. If I set x plus 7 equal to 0, what is my 0? -7. If I have 2 of those, that means my multiplicity is with 2. I have an even multiplicity, so what does that affect whenever I'm looking at it on the graph? It's going to bounce. So even multiplicities are going to bounce. If I set 2x plus 1 equal to 0, what is that x value? Or what is that 0? Negative 1/2. What is its multiplicity? 1, right? There's only the one of them. So its effect on the graph is going to pass. Right? It's going to pass through the x-axis. And then we have x minus 4. We've got 3 of those. What is it? 0? First off. 4. How many do we have? 3. Do we pass or bounce? Pass. Right. And again, we can check. We plug it right into the calculator. So we got x plus 7. That's squared times 2x plus 1. And x minus 4 cubed. So if we graph it, I don't know why my calculator did that. Did that yesterday too. But we pass at the 1/2. We pass at the 4. And I don't know why my calculator is skipping that -1, but it's just not showing up. Or that -7. I mean, it's halfway there and then the line disappears. I don't know why my calculator is different. But let's look at our next one. This time, rather than it being in factored form, they give it to us in standard form. But we also know how to find our zeros and everything else from the graph. Right? So let's just plug it in. Go to your y equals. This time we've got x to the 4th minus 2x squared, or 2x cubed, excuse me, minus 8x squared. And yours did it too? That is weird. I don't know why it's doing that. So here's our graph on this one. So its shape. Kind of W shaped. This is at 2. That one's at 4. So what is its zeros, number 7? Where do we cross the x-axis? So we have -2, or 0, and 4. What is the multiplicity at -2? 1, right? We just passed through. So the effect, again, we're looking at the graph, it passes through, right? What about at 0? What happens at 0? It bounces. So what does that mean the multiplicity is going to be? 2, could be 4, could be 6 or 8, but we're going to say 2. And then what about at 4? Passes. So we're going to say its multiplicity at least is 1. Now we started off with a 4th degree polynomial, so x to the 4th. Well, let's count up our multiplicities. They should add up to 4. We got 1, 2, 3, 4. So that makes sense. So then our last one, number 8. A polynomial function has a 0 at -6, multiplicity of 2, and 2, multiplicity of 1. Write a polynomial function in standard form that could represent this function. So how could we write that in standard form? First, how do we turn a 0 into a factor? right? We know that x equals -6. And we've got 2 of those. We also know that x equals 2. So this was given from the problem. Right now we have this. How do we turn it into something that looks like this? X plus 6, right? We need to move our 6 to the other side, and we also need to move our 2 to the other side. So that's going to get us x plus 6 as a factor. We've got 2 of those, and then we also have that x minus 2. So now we have our equation in factored form. So then the next thing we want to do is we want to turn it into standard form. Turn it into standard form, we're going to take all of our factors, multiply them together. So we got to FOIL it. X times x gives us x squared plus 6x plus another 6x plus 36. Now before we multiply by our x minus 2, we can combine these two, right? It's going to get us a 12x. I'm just going to go ahead and rewrite it. So again, I can use that box method. Multiply to get inside of our box. X times x squared gives us x cubed. X times 12x. 12x squared. X times 36 is 36x. Then you go to your next row. Negative 2x squared, negative 24x, and negative 72. Combine your like terms to get back outside the box. We only have one x cubed. Negative 2 and a positive 12 is going to leave me with a 10x squared. 36 minus 24 leaves me with a 12x minus 72. So there is our equation, right? We were given 3 zeros. We have a degree 3 polynomial. Of course, if we factor back, we get back to those zeros. And a quick way to check, let's graph it. Let's see if we did multiply it all correctly. So our equation is x cubed plus 10x squared plus 12x minus 72. And if we graph it, our graph comes up, it bounces at that negative 6, passes through at 2. Say we did it. Our values make sense. They look the same as the graph should. Any questions on multiplicities and zeros? So that's it.